When we do experiments in science, we want to be accurate and precise. Now, those two vocabulary terms are similar, but there's a subtle difference between the two. When we think about accuracy, we define it as how close our measured value is to the true value or the real value, which means that if we were having a dart competition and you have 5 darts and you want to be accurate, you want all your darts to land very, very close to the center. Okay? If you have a dart that lies very far from the center, away from the rest of your values, we would call that particular one whoops, an outlier. And when we do our averages to see how accurate we are, and we take the average of our 5 shots, we would actually exclude the outlier and just average out the 4 that we actually hit in the middle. Okay? And if we were to average our 4 trials instead of the 5 trials, we would find that yes, we were fairly accurate because we were very close to the bullseye. I just realized I spelled outlier wrong. It's been a rough morning. Precision describes the repeatability of a result. For example, if you have 5 darts, okay, and you hit all 5 darts somewhere away from the middle, but all 5 darts were very, very close together, we would say that you are a very precise dart player because all 5 of your shots consistently hit the same area. Okay? So accuracy describes how close you are to the real value, in this case, in this example, the bullseye, and precision describes how close each of your trials are to each other. And in science, we want to be both accurate and precise in anything that we do. We always run 3 trials and experiments that we do and get the average, excuse me, to see what our result is. Looking at the 3 data sets here, which data set appears to be the most precise? Data set A. We say data set A is the most precise because all 3 trials fall very, very close to each other. If I were to say, actually the real value is 2, and I asked you which data set is the most accurate, then we would go with option C, because that's the closest one we have to our true value of 2. Okay. So let's continue on with the dartboard analogy. Let's look at the first dartboard. In the first dartboard, we would say that our results are not accurate because there's nowhere near the center of the dartboard, but we would say that the data set is very precise. In our second set, because our darts fall very, very close to the middle, we say this is a very accurate data set. And because they're all very close to each other, we will say this is very precise. And this is what we always want in science. In our third dartboard, we see that each of our shots are nowhere close to the middle, so it's not accurate. And they're nowhere close to each other either, so they're not precise. So that is what we try to avoid in science. We don't want to be inaccurate and imprecise. In an experimental sense, the first scenario, we would say you have very good skill doing your experiment. However, there is something inherently wrong about your experimental setup that makes your answers all fall away from the actual answer. So our first situation represents good experimental skills on the part of the scientist, but something is wrong with the experimental design. Our second set, we would say we have very good skill and our experimental design is very good for what we were trying to do. And then our third set represents, well, our experiment sucks. We've totally designed it wrong. We couldn't get the answer that we wanted to get. And also your lab tech sucks too, because he or she couldn't get results close to each other at all. Alright, accuracy. How accurate we are, we can measure that as relative error, something called relative error, or it's also known as percent error. Okay, RE or percent error is equal to your experimental value or your result. I'm going to write it all out. okay, minus the true value, or what we call the theoretical value, all divided by the theoretical value, because you were comparing how far you, did I spell that wrong again? Theoretical, how far you are to the true value. It's a rough morning indeed. We do that and then we multiply that by 100. So for example, if a pencil is 12.56 centimeters long, but you measure it as 11.99, what is the error to your measurement, or how off are you? So you can say RE, or percent error, up to which we prefer, percent error. We take the experimental value, which is 11.99, because that's the one you measured from your experiment, and we subtract by the true value, or theoretical value, which is 12.56. We divide that by the true value, or theoretical value, which is 12.56, and we multiply that by 100%. When we do this calculation, 11.99 minus 12.56 divided by 12.56 times 100, we get negative 4.54. I'll try one more percent. What that means is your experiment was off by 4.54%, or you had a 4.54% error. That negative sign just says that you were shallow. You went on the small side, and you were too small by 4.54%. Sometimes you will see textbooks and other sources describe percent error as the absolute value of the top part divided by the bottom, so that their percent error is always going to be a positive value. And that's okay too. It's going to be up to you whether you want to say that your results were negative 4.54% off, or you can say it was under 4.54%. Whether you have the negative sign there or not, that is not a problem. So I don't actually mind if you want to report everything in positives, or you want to keep that negative sign in there. And that is how you determine how accurate your results were, and the difference between accuracy and precision. One more final thought to that. When you are using an instrument, we say that if you were able to measure something to a lot of decimal places, we say that value is more accurate and precise. Okay? So let's go back in our notes and let's examine what I mean by that. Take a look at the rulers, if you will, B and C. Ruler B would give you a less accurate of a measurement than ruler C, because the value you get from ruler B has 1 decimal place, where C can get you to up to 2 decimal places. So the more decimal places an instrument provides, the more accurate your answer is going to be. Okay? We can also say that ruler C is more precise than ruler B. If I have 5 people do a measurement with ruler B, they might say 2.5, 2.6, or 2.4, depending on the person, which means the repeatability is not as good. If we were to look at ruler C, if I were to give that to 4 or 5 people, most of them, or I should hope all of them, are going to say 2.4, and the value that they disagree upon is going to be that second decimal place, which means that the repeatability of our measurements are going to be better. They're going to be closer, because they will only differ by a 0.01, versus in ruler B, they will differ by a 0.1. Okay? And that concludes the discussion on accuracy and precision. Gu out.